Section 10 of the Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 2, edited by Francis Rolt Wheeler. Geology. Chapter 5, Development of Modern Knowledge, Part 2. Lyell's function was mainly that of a critic and exponent of the researches of his contemporaries, and of a philosophical writer thereon, with a rare faculty of perceiving the connection of scattered facts with each other and with the general principles of science. As Ramsay once remarked, "We collect the data, and Lyell teaches us to comprehend the meaning of them." But Lyell, though he did not, like Sedgwick and Murchison, add new chapters to geological history, nevertheless left his mark upon the nomenclature and classification of the geological record. Conceiving, as far back as 1828, the idea of arranging the whole series of tertiary formations in 4 groups, according to their affinity to the living fauna, he established, in conjunction with the Shays, who had independently formed a similar opinion, the well-known classification into Eocene, Miocene, and Pliocene. The scheme was a somewhat artificial one, and the original percentages have had to be modified from time to time, but the terms have kept their place, and are now firmly planted in the geological language of all corners of the globe. So far, no complete subdivision of the immense complex of strata between the crystalline schists and the coal measures had been attempted, and it was this gigantic task that the 2 British geologists, Adam Sedgwick (1785 to 1873) and Roderick Murchison (1792 to 1871), set themselves to accomplish in the British area. Unfortunately, the scarcity of fossils made it still impossible for Sedgwick to establish paleontological subdivisions. Murchison was more fortunate. While his colleague was engaged in the examination of the oldest group of the transitional series, Murchison began his investigation of the series in descending order from the upper members to the lower. He examined the exposures of Old Red Sandstone and the rocks immediately below it, which occur on the eastern and southern borders of Wales. Murchison found fossils in abundance, and in a couple of years was able to lay before the Geological Society a complete paleontological sequence in the upper portion of the transitional formations. At first, Murchison had called these higher members examined by him an Upper Fossiliferous Greywacke series, but in the year 1835, in compliance with the strongly expressed wish of Elie de Beaumont, he proposed the name Silurian system as a special designation for the upper members, and as the older members of the transitional series examined by Sedgwick in Cumberland and North Wales could not be identified with any of the members of the Silurian system of Murchison, the term of Cambrian series was proposed by Sedgwick in 1836 for these older members, and this term was accepted by Murchison. In the year 1839 Murchison published his great work, The Silurian System, wherein the results of his researches, extending over 6 years, were admirably elucidated. After a short statement regarding the younger geological formations, and a more detailed account of the English Carboniferous formation, the Mountain Limestone, and the Old Red Sandstone, Murchison passes to the special description of the Silurian system in South Wales and the adjoining counties of England. With great accuracy he depicts the stratigraphical relations, the lithological characters of the rocks, the contents of fossils and minerals, and the occurrences of volcanic rocks. A special paleontological part with 27 quarto plates is devoted to the description of the characteristic fossils by L. Agassiz, Sowerby, and Lonsdale. Numerous colored sections help to demonstrate the tectonic relations of the district. Murchison distinguished 3 chief divisions in the Silurian system: Upper Silurian, comprising the Ludlow rocks and Wenlock limestone; Lower Silurian, comprising the Carderock sandstone and Llandeilo flags; and Cambrian. He found it impossible at the time to fix a definite paleontological horizon as the lower limit of the Silurian system, and Sedgwick also could not assign any paleontological or other feature which would determine the upper limit of the Cambrian series. Nevertheless, the recognition of the Silurian and Cambrian systems was one of the most important advances that had been made in stratigraphy. There still remained, however, a thick group of strata in the Wernian transitional series, which could not be allotted to either of the newly defined systems. Continued researches on the Paleozoic formations led Murchison to conclude that the Cambrian deposits examined by Sedgwick in North Wales contained no fossils different from those of the Lower Silurian, and that the Cambrian system was identical with the Lower Silurian. Murchison made known this opinion for the first time in a presidential address which he delivered at the Geological Society. Sedgwick was deeply hurt, and immediately began a new investigation of Wales, in which he was assisted by the paleontologist Salter, and in 1852 he upheld the independence of the Cambrian series. Murchison was not persuaded by Sedgwick's results, and demanded a paleontological formation for the Cambrian system. The members of the Geological Survey, to whom the investigation of Wales was entrusted, followed the views of Murchison. The Cambrian system disappeared from the official maps, and the color for Silurian rocks was carried over the whole of the area previously allotted to the Cambrian system. Sedgwick, embittered by the want of recognition for his Cambrian system, published (1851 1855) a large work on the divisions and the fossils of the British Paleozoic deposits, and protested in strong terms against the views held by his former friend and fellow worker Murchison. While this dispute was in progress in Britain, a remarkable series of investigations by Johann Brande (1799 1883) had made known the extraordinary abundance and variety of Silurian fossils in Bohemia. The distinguished observer not only recognized the equivalents of Murchison's Upper and Lower Silurian series, but found below that series a still older group of strata, characterized by a different assemblage of fossils, which he termed the first or primordial fauna. It was ascertained that representatives of this fauna occur in Wales among some of the divisions of Sedgwick's Cambrian system, far below the Landilio group which formed the original base of the Silurian series. Eventually, therefore, since the death of the two great disputants, there has been a general consensus of opinion that the top of the Cambrian system should be drawn at the upper limit of the primordial fauna. The vast and varied series of rocks which have now been ascertained to underlie the oldest Cambrian strata have undergone much scrutiny during the last half-century, and their true nature and sequence are beginning to be understood. The first memorable onward step in this investigation was taken in North America by William Edmund Logan (1798 1875). He recognized the existence of at least 3 vast systems older than the oldest fossiliferous formations. He may be said to have inaugurated the detailed study of pre-Cambrian rocks. Subsequent investigation has shown the structure of the regions which he explored to be even more complicated and difficult than he believed it to be, and various important modifications have been proposed in his work and terminology by the able geologists of Canada and the United States who have continued his labors. But he will ever stand forward as one of the pioneers of geology, who, in the face of incredible difficulties, first opened the way towards a comprehension of the oldest rocks of the crust of the earth. Charles Darwin (1809 1882) contributed several valuable works to the literature of geology. The 2 geological chapters in his Origin of Species produced a great revolution in geological thought. To most of the geologists of his day, Darwin's contention for the imperfection of the geological record and his demonstration of it came as a kind of surprise and awakening. They had never realized that the history revealed by the long succession of fossiliferous formations, which they had imagined to be so full, was in reality so fragmentary. And yet, when Darwin pointed out this fact to them, they were compelled, sometimes rather reluctantly, to admit that he was right. Lord Kelvin (Sir William Thomson, 1824 1907) attributed great importance to the enormous pressure existing in the interior of the earth and the consolidation of the nucleus from this cause. He ascribed to the body of the earth a degree of rigidity intermediate between that of steel and of glass. Starting from the nebular theory, Lord Kelvin supposed that the cooled and thereby heavier masses sank inward and formed an initial central nucleus, which always extended toward the periphery as the earth's mass continued to cool, until finally almost the whole earth became rigid. Sir Andrew Crombie Ramsay (1814 1891), the noted Scotch geologist, devoted his attention to the physical side of geology. His dislike for paleontology and petrology sometimes led him into serious theoretical errors, thereby impairing the value of his work. His book on The glacial origin of certain lakes in Switzerland set forth the theory that certain lake basins had been scooped out by glaciers, now melted away. This book aroused considerable interest and controversy. This hypothesis has not yet been disproved, but it has failed to gather its most ardent supporters from the ranks of those who have an intimate personal knowledge of the Alps. In Austria and Switzerland, Suess, Hochstetter, Neumer, Studer, Agassiz, and others were making themselves famous. Suess's contributions to geology have opened up a new path in geological inquiry, and led the formation for what is now frequently termed the New Geology, dealing with the construction and relations of continents and mountain ranges, the dynamics of volcanoes and earthquakes, and the general movement of the earth's crust. In 1885 he began his Antlitz der Erde, which is a masterful exposition of the relations of the dominant features of the earth's surface, and the first luminous effort to correlate their multiform aspects and to give to them their true geological expression. He is one of the recognized authorities on earthquakes and volcanoes. Jean-Louis Rudolph Agassiz (1807 to 1873) was born in Switzerland, and rose to distinction by his scientific work in Europe, but he went to the United States when he was still only 42 years of age, and spent the last 27 years of his life as an energetic and successful leader of science in his adopted home. His fame is thus both European and American, and the geologists of New England, not less than those of Switzerland, may claim him as one of their most distinguished worthies. His fame as a geologist is due to the important part he took in founding the modern school of glacial geology. Tracing the distribution of the erratic blocks above the present level of the glaciers, and far beyond their existing limits, he connected these transported masses with the polished and striated rock surfaces which were known to extend even to the summits of the southern slopes of the Jura. He was led to conclude that the alpine ice, now restricted to the higher valleys, once extended into the central plain, crossed it, and even mounted to the southern summits of the Jura chain. Before Agassiz took up the question, there were two prevalent opinions regarding the transport of the erratics. One of these called in the action of powerful floods of water, the other invoked the assistance of flowing ice. Agassiz combated these views with great skill. His reasoning ought to have convinced his contemporaries that his explanation was the true one, but the conclusions at which he arrived seemed to most men of the day extravagant and incredible. Even a cautious thinker like Lyell saw less difficulty in sinking the whole of Central Europe under the sea, and covering the waters with floating icebergs, than in conceiving that the Swiss glaciers were once large enough to reach to the Jura. Men shut their eyes to the meaning of the unquestionable fact that, while there was absolutely no evidence for a marine submergence, the former track of the glaciers could be followed mile after mile by the rocks they had scored and the blocks they had dropped, all the way from their present ends to the far distant crests of the Jura. He, moreover, demonstrated the identity of the phenomena in Britain with those in Switzerland, and claimed that not only glaciers once existed in the British Islands, but that large sheets of ice covered all the surface. These, and the subsequent researches and glacial monographs of the great Swiss naturalist, started the study of ancient glaciation. At first his conclusions had been regarded as rank heresy by the older and more conservative geologists of the day. Von Buch could hardly contain his indignation, mingled with contempt, for what seemed to him the view of a youthful and inexperienced observer. A. von Humboldt also threw cold water upon the ardor of his young friend. But by degrees the opposition waned, and Agassiz had the satisfaction of seeing his most doughty opponents come over one by one to his side. William Nicol was a lecturer on natural philosophy at Edinburgh in the early part of the last century. Among his inventions was the famous prism of Iceland spar that bears his name. Every petrographer will acknowledge how indispensable this little piece of apparatus is in his microscopic investigations. He may not be aware, however, that it was the same skilful hands that devised the process of making thin slices of minerals and rocks, whereby the microscopic examination of these substances becomes possible. Yet for a quarter of a century geologists took no notice of the opportunities put in their way by William Nicol. When Nicol died, his instruments and preparations passed into the hands of the late Mr. Alexander Bryson of Edinburgh, who, having considerable dexterity as a manipulator, and being much interested in the process, made many additions to the collections which he had acquired. At last Henry Clifton Sorby came to Edinburgh, and had an opportunity of looking over the Bryson collection. He soon began to put the method of preparing thin slices into practice, made sections of mica schist, and found so much that was new and important, with a promise of such a further rich harvest of results, that he threw his whole energy into the investigation for several years, and produced at last, in 1858, the well known memoir on the microscopical structure of crystals, which marks one of the most prominent epochs of modern geology. Sorby, for the first time, showed how, by means of the microscope, it was possible to discover the minute structure and composition of rocks, and to learn much regarding their mode of origin. In recent years some excellent work has been, and is constantly being done, along the line of geological investigation. Geological surveys are being conducted under the supervision of the governments of the United States, the individual states, and the countries of Europe, and prominent present-day geologists are writing invaluable books on geological subjects. Important contributions to the history of geology have been made by the fluent pens of Sir Archibald Geikie and Karl von Ziehtel, to whose works much of the value of the foregoing may be ascribed, and each department of geology now is in the hands of able specialists. Geology and paleontology give great promise for the 20th century. In another 100 years the whole surface of the earth will perhaps be so well known that works on comparative topographical geology will be fully accomplished along the lines which Edward Suess has so ably initiated in his Antlitz der Erde. If at the same time the structural and physical problems of the solid earth crust continue to be accurately investigated in all parts of the earth, it may be possible to determine the actual physical sequence of events in the origin and development of this planet. End of Section 10. Recording by Todd.